Let S be a non-empty bounded subset of R with supremum of S equals to capital M, infimum of S equals to small m. Then prove that the set T elements mod of x minus y such that xy belongs to S is bounded above. And also show that supremum of T equals to capital M minus small m. So let first we show that T is bounded above. Let small x belongs to capital S. Therefore, then small m less than equals to x less than equal to capital M. Since small m infimum of S and capital M supremum of S, so obviously every element of S is greater than or equal to infimum and less than or equal to supremum. Let y belongs to S. Therefore, obviously small m less than equals to y less than equals to capital M. We name it 1, we name it 2. From 1, since from 1 small x less than equal to capital M, and from 2 minus y less than equal to minus m. Now small m less than equal to y. This means minus m greater than equals to minus y, that is minus y less than equal to minus m. So adding x minus y less than equal to capital M minus small m, we name it 3. Again from 1 small x greater than small m and small y less than equal to capital M. Therefore minus y greater than equals to minus capital M. Adding x minus y greater than equals to small m minus capital M equals to, this will be minus of capital M minus small m. Therefore x minus y greater than equals to minus of capital M minus small m. We name it 4. From 3 and 4 minus of capital M minus small m less than equals to x minus y less than equals to capital M minus small m implies mod of x minus y less than equals to capital M minus small m, because we know minus epsilon less than equals to x less than epsilon implies mod of x less than equals to epsilon, using this simply. Now we know what is the definition of upper bound. A real number u is said to be an upper bound of a set A if every element of A is less than or equal to u. That means x belongs to A implies x less than or equal to u. Then u is said to be upper bound of A. Now here mod of x minus y is an element, arbitrary element of T. So every element of T less than equals to capital M minus small m. Therefore capital M minus small m is an upper bound of T. And what is the definition of bounded above? A set T, a set A, suppose a set A is said to be bounded above if A has an upper bound. Now T has an upper bound, so therefore T is bounded above. A set is said to be bounded above if it has an upper bound. So obviously T is bounded above because T has an upper bound. So we prove T is bounded. Next, we have to prove the supremum of T equals to capital M minus small m. We have to prove that supremum of T equals to capital M minus small m. That is, we have to prove that capital M minus small m is the least upper bound of T. That is, we have to prove that no upper bound of T can be obtained which is less than capital M minus small m. because we have to show that capital M minus small m is the least upper bound. So let small a belongs to S. Therefore, mod of a minus a belongs to T. Therefore, T is a non-empty subset of R. Subset of R. And we already proved that T is bounded above. And T is bounded above. Now, by supremum property of R, we know that every non-empty subset of R that is bounded above has a least upper bound, that is a supremum. So, T is a non-empty subset of R and T is bounded above. Therefore, by supremum property of R, sup T exists, that means supremum of T exists. We have to prove that no upper bound of T can be obtained, which is less than capital M minus small m. If possible, let small p be the upper bound of T, which is less than capital M minus small m. That is, P less than capital M minus small m is an upper bound of T. Therefore, capital M minus small m minus P greater than 0. We see that contradiction arises. We will see from this. Now, capital M minus small m, let capital M minus small m minus P equals to 2 epsilon greater than 0. Therefore, capital M minus small m minus epsilon equals to P plus epsilon. We name it phi. Now, since supremum of S equals to capital M, by the properties of supremum, there exists an element small x belongs to S such that small x less than equal to capital M, this x strictly greater than capital M minus epsilon by 2. We name it 6. Now, since infimum of S equals to small m, by properties of infimum, there exists an element small y belongs to S such that small m greater than equals to y strictly less than small m plus epsilon by 2. That is, we name it 7. So, from 6 and 7. From 6, x greater than capital M minus epsilon by 2. X greater than capital M minus epsilon by 2. And from 7, y less than M plus epsilon by 2. That means minus y greater than minus of M plus epsilon by 2. This means minus y greater than minus M minus epsilon by 2. Adding x minus y greater than capital M minus small m minus epsilon. Now, equals to, this is P plus epsilon by 5. Therefore, we get x minus y greater than P plus epsilon. We assume P is the upper bound of T. By definition of upper bound, mod of x minus y, every element of T less than equals to P. Therefore, mod of x minus y less than equals to p plus epsilon, obviously, where epsilon greater than 0. Therefore, p plus epsilon minus of p plus epsilon less than equals to x minus y less than equals to p plus epsilon. Then, because this should be satisfied, because p is an upper bound of t. So, but we get x minus y greater than p plus epsilon. This contradicts the fact that p is an upper bound of t. Because if p is an upper bound of t, then p satisfies this condition, and this implies this implies this. But we get x minus y greater than p plus epsilon. So, therefore, no upper bound of t can be obtained which is less than capital M minus small m. Therefore, capital M minus small m is the least of all upper bounds of t. Therefore, this is the supremum by definition. Therefore, supremum of t equals to capital M minus small m. Proved. If you like this video, please share and subscribe.